Hello friends, today we are discussing the frame of references. In the frame of references, there are two types of frame of reference. One is the inertial and another is the non-inertial. Inertial frame is nothing but unaccelerated frame of reference, while non-inertial frames are accelerated frames of references. We all know that motion is always relative. Motion of body has no meaning unless it is described with respect to some well-defined coordinate system. Thus, for example, if the velocity of a moving train is observed, it will be different for different observers, moving with different velocities. Let us suppose that a train moving with velocity 40 km per hour is observed by three observers A, B and C. A is standing on the earth, B with velocity 10 km, that B is moving with velocity 10 km per hour in the direction of motion of the train, and C moving with velocity 10 km per hour in a direction opposite to that of train. What is the observation? The observation is that the person A will observe the velocity of train to be 40 km per hour. B will observe it to be 40 minus 10, that is 30 km per hour, while C will observe it to be 40 plus 10 is equal to 50 km per hour. Also, person on the same train will observe it to be at rest. The velocity of the same train is different relative to different observers. Therefore, in order to describe the motion of an object, we must assume the existence of coordinate system. Such a system of coordinate axes relative to which the motion of an object is described is called a frame of reference. Thus, frame of reference is a system of coordinate axes which defines the position of a particle or an event in two or three dimensional space. As we know, the simplest frame of reference is the Cartesian coordinate system, in which the position of the particle is specified by three space coordinates x, y, z, then the position vector of the particle with respect to the origin, that is given by vector r is equal to ix plus jy plus kz, and all the three I, j, k are the unit of vectors along the three axes. For complete identification of an event, we require its position and time of occurrence. Therefore, in addition to the usual three spatial coordinates x, y and z, we required another coordinate, that of time t. A frame of reference with such four coordinates x, y, z, t is called space-time frame of reference. There is an infinite number of reference frames in the universe. Our Earth is itself a frame of reference. The other examples of the frame of reference may be considered to be the walls of the room, then the position of the stars along plumb line, the sun, etc. Newton introduced the idea of absolute space as a standard frame of reference, which which was later on discarded. So when a body is in a frame of reference, obeys the Newton's law of inertia and other laws of Newtonian mechanics, such a frame is called inertial frame of reference. In this case, no external force acts on the body. It is either rest or moving with constant velocity. A frame of reference moving with constant velocity relative to an inertial frame is also inertial, since acceleration of body in both the frames is zero, while velocity of the body is different but uniform. A frame of reference fixed in stars is an inertial frame. The Earth is not really an inertial frame of reference because of its orbital motion about the Sun and rotational motion about its own axis. In fact, anything which is capable of turning is not an inertial frame. Since force acting on it changes its direction, hence it is neither at rest or nor moving in a straight line with a constant speed with respect to such a frame of reference. However, the Earth may be assumed to be an inertial frame in many ways. So there are two types of inertial frame and non-inertial. Initially we are discussing the inertial frames of references. In this case, as we already discussed, those frames of references in which Newton's first and second law hold true are called inertial frames. They are also known as Newtonian or Galilean frames. In such frames, if a body is not acted upon by any external force, it continues its state of rest or moves with constant uniform velocity. It means that in an inertial frame, the acceleration a is zero. As how it gets, a is equal, the vector a is equal to d2r by dt square is equal to 0. In component form, this equation can be written as d2x by dt square is equal to 0, d2y by dt square is equal to 0, d2z by dt square is equal to 0. So let us consider an inertial frame S and another frame S dash. Here it is, this is the frame of reference S and the red color showing the S dash, which is moving with constant velocity v relative to S. Initially means at time is equal to 0 if the position of origin of the two frames coincide here, then in the two frames of the position vectors of any particle p at any instant t can be related by following relation, by following expression. So the position vector is equal to o dash plus r dash, or r is equal to vt plus r dash, or we can write r dash is equal to r minus vt. As v is constant, then d2r dash by dt square is equal to d2r by dt square. So this is nothing but the acceleration. Two accelerations are there. So we can write a dash is equal to a. Here the particle experiences the same acceleration in two frames, which are moving with constant relative velocity. Now if the acceleration of the particle in a frame S is 0, its acceleration in S dash is also 0. But S is an inertial frame, S dash should also be inertial. So we can easily conclude that if a frame is an inertial frame, then all those frames which are moving with constant velocity relative to the first frame are also inertial. For this purpose, we can take the example. In movies, when the camera is focused on the actor and zoom out, in that case, by observing, we clearly identified by zooming the actor's image, simultaneously the another frame of reference behind that actor, the scene scenery is there, also zooming. In that case, your eyesight is also changes their retina. When the light is acting on your eyesight, the contraction and expansion takes place in your eyesight. So all these are frames are inertial and they are related with each other. So the inertial frames are unaccelerated frames, because if the frame is accelerated, a particle whose velocity is constant and will appear accelerated in this frame. If the observed acceleration of a body of mass m in an inertial frame is a, then in such a frame the force is given by F is equal to m into a. In case of accelerated reference system, F does not equal to ma. If a is the acceleration as observed in the non-inertial system, the motion of body itself has no meaning unless we do not know with respect to which this motion has been measured. This led Newton to think about the absolute space. According to Newton's, the absolute space represents that the system of reference relative to which every motion should be measured. The experience tells that fixed stars are approximately stationary relative to the absolute space, because a body sufficiently far removed from celestial matter always moves with a uniform velocity relative to the fixed star. Thus, this absolute system is an inertial frame of reference. It is also clear that the law of inertia is valid in all those of reference system which are moving with constant velocity relative to the absolute system. Hence, all these frames of reference are inertial. Among these reference frames, one is absolute system, which is stationary relative to the fixed star. But the view of the validity of the law of inertia, all the frames of reference will be completely equivalent. If a frame is fixed on the earth, this frame will not be inertial because the earth is spinning about its axis and simultaneously it is moving in its orbit round the sun. For many purposes, the earth is fairly good approximation to an inertial frame. But due to the rotation of earth, a particle at rest on the surface of the earth experiences centripetal acceleration, which cannot be entirely neglected for all purposes. So this is the inertial frames of reference. Now we are discussing the non-inertial frames and some forces. That force is called as fictitious force. The fundamental physical laws and principles are identical in all inertial frames of reference. If, however, a frame of reference is accelerated relative to an inertial frame, the form of the fundamental physical laws, such as Newton's second law, becomes completely different. Such accelerated frames of reference are called non-inertial frames. In fact, all the accelerated and rotating frames are non-inertial frame of reference. Therefore, the non-inertial frames may be defined as those frames of reference in which Newton's first and second law are not valid. Thus, if the observed acceleration of a body of a mass m in a non-inertial frame is a vector a, then the formula, that is vector f is equal to m into vector a, and does not hold true in this reference frame. For that purpose, consider the two frame of reference S and S, two systems S and S dash. The latter moving with an acceleration a0 here. So S is in motion relative to S. S dash is in motion relative to S. If we consider the first frame, this frame, to be inertial, then second will be non-inertial. If we are considering this frame is inertial, then this frame is non-inertial, because we are considering this inertial frame is stationary while S is moving relative to S dash, or vice versa. Thus the non-inertial frame S dash may be supposed to be moving with an acceleration a0 relative to the inertial frame S. Then the particle P, which are at rest with respect to the frame of reference S, will appear to move with an acceleration minus a0 with respect to frame of reference S dash. Thus, in a frame of reference S dash, a force is minus ma0. So with respect to frame S dash, will appear to be acting on the particle of mass m. Such a force, which does not really act but appears to act only due to the acceleration of the frame of reference is called the fictitious apparent or a pseudo force. This pseudo force on the particle P of the mass is given by, this is the first force, that is F is equal to m into A, but this pseudo force is minus m into A 0. Now if this mass m has an acceleration AI in the inertial frame S, then the force which acts on this mass in a frame S is F is equal to m into AI. Hence the force acting, total force acting on the particle as observed in a frame S dash, and is given by F is equal to MAI minus MA0, where AI minus A0 is equal to A, that is the acceleration of the particle as observed in the frame S dash. Combining this equation with this equation and this equation, we get the F dash is equal to MA is equal to MAI minus MA0. So this here F dash is the force that describing in the frame S dash. So we get the F dash is equal to F plus Fp. So this is the fictitious or pseudo forces. What is the pseudo force, or how can explain, or what are the examples of fictitious force? For that purpose, consider a particle of mass m at rest inside a lift falling freely under gravity. Then the fictitious force acting on it. What is the fictitious force? Fp is equal to minus mg. The real force on the particle due to the attraction of the earth. So F is equal to mg. Then what is the resultant force on particle as observed by the observer in the lift? That frame is what? The frame is moving frame. So as per your formula, F dash is equal to F plus Fp, mg minus mg. So we get the fictitious, the force, the resultant force on the particle is 0. That is, the particle is weightless and thus appears to remain suspended in space. Thus the body is unaccelerated in this frame. This fictitious force is called as a centrifugal force and is obviously directed away from the center. It is an account of these forces that an observer in a rotating frame find mysterious forces not accounted for by any origin of force, throwing things outwards towards the wall. So this is the inertial and non-inertial frame of references. The non-inertial frames, in simple language, we can say that when a body is accelerated in a frame of reference, the frame of reference is called non-inertial frame of reference, or in simple language, the laws of inertia are not valid for an accelerated frame of reference. Or we can say that the Newton's laws are valid in non-inertial frames. The Newton's laws are not valid. In simple language, the inertial frame may be defined as the frames in which Newton's laws are valid, and in non-inertial frames, the Newton's laws are not valid. So this is the inertial and non-inertial frame of reference. Thank you very much for the watching this video. Thank you.